Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to the fifth lecture of Mechanics of Solids. In this lecture, we will discuss stress from the perspective of practical applications. We will try to explore why is it necessary to limit the stress to an allowable value and how this concept is utilized in the design of various types of connections. To properly design a structural member or mechanical element, it is necessary to restrict the stress in the material to a level that will be safe. To ensure this safety, it is therefore necessary to choose an allowable stress that restricts the applied load to one that is less than the load that a member can fully support. It means that we need to first evaluate the capacity of the member, keeping in mind its material properties as well as its geometrical properties. Then the applied stress should always be less than the amount of stress that a material can bear based on its own inherent properties. There are many reasons for doing this. For example, one of the main reasons is the fabrication errors. Most of the time, the uh, designed or the constructed member is having a deviation in its measurements from the design measurements. Another reason for this is excessive loading. Obviously, we design for a particular load, but most of the time, the applied loading, especially on bridges or in road networks, is more than the load for which the structure has been designed. And this is accounted by using a factor of safety, which we will discuss in the coming slides. Sometimes another reason to use this concept of allowable stresses is the unanticipated loading. Any kind of impact, natural disasters such as floods, hurricanes, earthquake, etc., can cause a huge amount of excessive loading than for which the structure has been already designed. Another main reason of this thing is the deterioration of structures due to weathering effects and the uh, indigenous properties of concrete, which results in the loss of its strength and other mechanical properties. One method of specifying the allowable load for a member is to use a number called the factor of safety. The factor of safety is the ratio of the failure load to the allowable load. The failure load is found from the experimental testing of the material, and the factor of safety is selected based on the experience so that the above mentioned uncertainties are accounted for when the member is used under similar conditions of loading and geometry. If the load applied to the member is linearly related to the stress developed within the member, as in the case of using normal stresses or shear stresses, then we can also express the factor of safety as the ratio of the normal failure stress to the normal allowable stress, or to the ratio of the shear failure stress to the shear allowable stress. In any of these equations, the factor of safety must be greater than 1 in order to avoid the potential for failure. However, specific values depend on the types of materials to be used and the intended purpose of the structure or machine. For example, factor of safety used in the design of aircraft or space vehicle components may be close to 1, it's usually 1.25 or 1.35, in order to reduce the weight of the vehicle. In the case of nuclear power plant, the factor of safety for some of its components may be as high as 3 due to uncertainties in loading and material behavior. In many cases, the factor of safety for a specific case is usually found from the design codes and the engineering handbooks. These values are intended to form a balance of ensuring public and environmental safety and providing a reasonable economic solution to design. By making simplifying assumptions regarding the behavior of the materials, the equations discussed in the previous lecture for the normal stress and the shear stresses can often be used to analyze or design a simple connection or mechanical element. In particular, if a member is subjected to normal force at a section, its required area at the section can be determined from this equation, in which the applied normal load is divided by the allowable normal stress. If the section is subjected to shear stress, then its allowable area can be determined using this equation, in which the applied shear force is divided by the allowable shear allowable shear stress. On the other hand, the allowable stress used in each of these equations is determined either by applying a factor of safety to the material's normal or shear failure stress, or by finding these stresses directly from an appropriate design code. Now let's consider some examples. In this first example, this normal force is being applied on this I-beam, and in order to determine the area of this particular beam, the required area of this particular beam, we need to use this equation. Again, sigma allowable must have been determined from the required codes. In this example, this concrete rod is being attached to this face by using some kind of epoxy resin or glue, and we can determine the the area of the rod required based on the allowable shear stress value of that particular glue. This is the third example, in which again this bolt is being subjected to shear stresses by the application of these forces on these two plates, and in order to determine this the area of this bolt, we can use the applied load divided by the tau allowable or the allowable shear stress for this particular bolt. When solving problems using the average normal and shear stress equations, a careful consideration should first be made as to choose the section over which the critical stress is acting. Once this section is determined, the member must then be designed to have a sufficient area at the section to resist the stress that acts on it. This area is determined using the following steps. First of all, we need to determine the internal loading. For this, section the member through the area and draw a free body diagram of the segment of the member. The internal resultant force at the section is then determined using the equations of equilibrium. After that, determine the required area using the equations which we have discussed in the previous slide, which are the normal load divided with the normal allowable stress, or the shear load and divided by the shear allowable stress. This is our first example for the design of connections. In this example, we have been given an arm that is subjected to the loading shown in this figure. We have to determine the required diameter of the steel pin at C if the allowable shear stress for the steel is 8 ksi. So first of all, our first step should be to draw a free body diagram. If we draw a free body diagram of this element here, we came to know that we do not know how much force is being applied at this point, FAB, or the second support, and the first support is at C, which is actually an inclined support. Let me use a pen. This was an inclined support here, but we know that using the principle of superposition, we can divide this inclined force in these two, in the respective horizontal and vertical components. Why have we done so? Because it's usually much easier to work in this xy coordinate as compared to any kind of inclined coordinate. Thus, we are having this free body diagram, and using summation of forces and summation of moments, we are going to determine first of all the applied forces at the point C or the reaction forces at the point C to determine the diameter of the steel pin that is required to support this this combination of forces. Now, using this free body diagram, Let's first apply the summation of moment at this point C. If we apply summation of moment at point C, we can see that only the vertical component of this force of 5 kip will apply a moment at C. Along with this, a moment will be applied with this by this force FAB and this force of 3 kip here. Thus, taking anticlockwise moments as positive, the force FAB comes out as 3 kips. Now, using the summation of forces in the x direction and the summation of forces in the y direction, we have determined the two unknown components of the force at point C, which comes out as Cx is equal to 1 kip and Cy is equal to 6 kips. Using the concept of resultant forces, we can determine the resultant force at point C as 6.082 kips. Now, if we closely look at this connection, we can determine that the pin at this location C is actually supported by two supports here. Thus, the total applied force of 6.082 kips is divided into half, and each face of this pin is supporting half of this applied force. Thus, if we need to determine the cross-sectional area, the applied force will be taken as half of this 6.082 kip, and using this concept of allowable stresses, we can determine the area as the applied load of 3.041 kip divided by the allowable stress of 8 kips, and cross-sectional area of this pin, required cross-sectional area of this pin comes out as 0.802 square inches. Obviously, from area, then we can determine this diameter using the simple concept of pi d square by 4. Thus, a pin having a diameter of 3 by 4 inch is suitable for supporting these applied forces. Here is our second example in which we have a fixed connected circular disc to a rod and a force of 20 kN is applied at the rod at this end. We need to determine the diameter of the rod and the thickness of the disc that is needed to support this load of 20 kN. If we take a closer look at this assembly, we can easily see that this rod is actually supporting a normal stress, and this disc will be subjected to shear stress. Thus, it's given to us that the allowable normal stress for the rod is 60 megapascal and the allowable shear stress for the disc is 35 megapascal. In this case, determining the diameter of the rod is quite simple. We just need to use this equation in which we divide the applied load of 20 kN by the allowable stress in the allowable normal stress in the rod, and we equate it to this area here, and using this simple formulation we can determine the diameter of the rod. However, in case of thickness of disc, we closely need to evaluate the area that is being subjected to shear stress. Here we can see that the area subjected to shear stress is can actually be determined by multiplying the thickness of the disc with the parameter of the disc, because this area, this small where the shear stress is being shown, is actually under the influence of the shear stress due to this applied force. Thus, the parameter of the disc can be determined as 2 pi into diameter, and in order to have it the area of this region, we need to multiply it with the thickness, and we equate it to the applied shear force divided by the allowable shear stress in the disc. And then using this formulation, we have determined here the required thickness of the disc, that comes out to be 4.55 millimeter. Let's begin our third example. This is a bit more involved, but it will elaborate all the concepts that we have studied till now more clearly. So we have been given this assembly here, in which this rigid bar AB is supported by an aluminium block at this point and a vertical bar AC at this point, and then it is subjected to a load of P. We need to determine, we have been given the the failure stress of the aluminium block, the steel rod, as well as the pins at point A and C. And we also need to keep this in consideration that the pins at A and C are in single shear. These are not in double shear as in our previous example. We need to determine the largest load P that can be applied to the bar. This means that first of all we will need to consider what is the allowable stress for the aluminium, steel, and these pins based on their material as well as the geometrical properties. So let's start our example. In the first step, we need to determine the allowable stress in steel, aluminium, and the shear at the of the pins. For this, we divide the failure stress by the factor of safety. This information has been provided in the given data of the example. This allowable stress for steel, aluminium, and shear comes out as 340, 35, and 450 megapascal respectively. In the next step, we draw a free body diagram of the given rigid bar. It comes out as two forces FAC and FB are the reaction forces in result of this applied load P. Again, using the summation of moments, we can determine the relation between these applied forces. Taking moment at B, we come out with the relation between P and FAC, and taking moment at A, we can obtain the relation between the applied force P and the reaction at B. These are these two respective relations. Next, we need to determine the value of P that creates the allowable stress in rod, block, and pins respectively. Thus, if we are considering rod AC, first we need to determine what is the allowable force in the rod AC. The allowable stress in the steel AC was 340 megapascal, and the area of rod AC has been given as the 10 millimeter square. So the obtained allowable force in AC is the 106.8 kilonewton. Using this equation 1, we have obtained that the rod based, if you are considering rod AC, the applied force can be 171 kilonewton. Now similarly, we need to determine the allowable force that the aluminium block can support, and using the same analogy, it comes out as 63 kilonewton. Again, if we use this equation B, we have obtained this 168 kilonewton as the force that can be applied at this location P, or which can be the value of P. In the final step of this example, we have to determine the force that can be supported by the pins in single shear. Thus, that pin can support a load of 114.5 kilonewton, and based on the equation of the previous slide, we have determined that these shear pins can support 183 kilonewton load being applied at point P. So by comparison, as P reaches its smallest value 168 kilonewton, the allowable normal stress will first be developed in the aluminium block. Thus, we need to limit P to 168 kilonewton if we avoid the failure of the aluminium block. If we summarize the lecture, what we have learned till now is that design of a member for strength is based on selecting an allowable stress that will enable it to safely support its intended load. Since there are many unknown factors that can influence the actual stress in a member, then depending upon the intended use of the member, a factor of safety is applied to obtain the allowable load the member can. Thanks for listening. You can ask your questions in the comments.